Hi everyone, I'm Dr. Surjit Singh. Today we'll talk about the Leetcode problem merge intervals. Let us begin. We are given a list of intervals. We are to merge the overlapping intervals. We will set up a graph of intervals as nodes having edges between the overlapping intervals. We are given a list of interval lists. We build a graph between these intervals as nodes. We define graph as a blank dictionary of lists and loop over all the pairs of intervals. For I is equal to 0, interval is 1, 3. For each I, j goes from I plus 1 to end. In order to check their overlap, we define a local function overlap. The two intervals a and b overlap if a0 is less than b1 and b0 is less than a1. As both the conditions are true, overlap returns true, so we create an edge between them. As the graph is non-directional, we save 2, 6 against 1, 3 and 1, 3 against 2, 6. The key in a dictionary cannot be mutable. We convert keys into tuples. 1, 3 does not overlap with 15, 18, nor with 6, 10. And 2, 6 does not overlap with 15, 18, but does overlap with 6, 10. That gives two more entries in the graph. The last pair of intervals do not overlap and we return the graph and save it in the main function. After build graph, we call the function getComponents. We define a set visited. The number of components in the beginning is 0. Nodes in components is a default dictionary of lists. We process all the intervals one by one. If the interval is not visited, we call the local function markComponentDFS. We copy the starting interval in a list named stack. While stack is not empty, we pop out node from stack as a tuple. Node 1, 3 is not in visited, so we now add it there and add it in the nodes in component against n component, that is 0. Next, we extend stack by all nodes connected to the node 1, 3. In the next iteration, we pop out 2, 6. It is not in visited, so we add it there and add this as another node in the component 0 and extend stack by two nodes that are in the graph against 2, 6. In the next iteration, we pop out 6, 10. This is not in visited. We add it to visited and as another node in component 0. We extend stack by node 2, 6. We pop out 2, 6 from stack to node. It is already in visited, so we ignore it. Next, we pop out 1, 3 in node. It is also in visited, so we ignore it. Stack is now empty, so we come out of DFS function and increase number of components by 1. In the next iteration, 2, 6 is already visited, so we skip it and call DFS function for interval 15, 18 and copy it in list stack. We pop out 15, 18 to node, add it to visited and add it as a node of component 1. DFS call ends and we increase the number of components to 2. Last interval 6, 10 is already visited. Call to get components ends after returning number of components and nodes present in them. We start a for loop. In the first iteration, component is 0. We now call the function merge nodes. Parameters in merge nodes is a list of 3 nodes present in component 0. These 3 are overlapping intervals and we must merge these into one interval. Starting times of 3 intervals are 1, 2 and 6. Starting time of the merged interval is the minimum of these 3, which is 1. Maximum of 3, 6 and 10 becomes the end of the combined interval. which is added to a list. In the second call of merged nodes of component 1, for which there is only one interval. Therefore, no merging is needed, and we append this interval as such to the previous list. The for loop is over, and we return the list of merged nodes as the final answer. We have used a loop within a loop in building of the graph. In getComponents, we loop over intervals, and each time we process all its neighbors, which in the worst case is n. Both have time complexity of n squared. Merged nodes is linear, so the overall time complexity is of the order of n squared. In the worst case, all intervals may be overlapping, and the space complexity is of the order of n squared. So I think it is clear that sorting of the intervals will make the merging process quicker. Consider the same interval list. We perform sorting on begin times of intervals. Advantage of sorting is that only adjacent intervals can overlap with each other. We define merged as an empty list and process the intervals one by one. First time, the merged list is empty. So we append the interval in the merged list. In the next iteration, n time of the last entry in merged list is not less than the begin time of the current interval, so the two intervals overlap, and we process the else part in which we merged the two intervals by replacing larger of the two n times as the new n time of the merged interval. The next interval also overlaps with that we saved lately in the merged list, so the new n time becomes 10. In the last iteration, n time of the latest merged interval is less than the start time of the current interval, so there is no overlap, and the current interval is appended to the merged list as a new entry. After processing all the intervals, we return the merged list as the final solution. Time complexity of sorting is n log n. Merging of intervals is linear, that does not affect the time complexity. Sorting takes additional space of the order of n to save intermediate data. However, if we use the in-place sorting technique, temporary values are not saved. In this case, the space used in sorting is log of n. I hope you enjoyed the video. Thank you for your time. Please stay tuned for more such interesting videos.